This lesson is going to walk you through a heating curve. So by the end, you want to be able to create and interpret a heating curve, and you also want to be able to calculate the energy transferred when a substance changes state. So as something is melting or evaporating, we want to be able to calculate how much energy is needed in order to do that. So the first thing is, what is a heating curve? So you have a picture of a heating curve on your graph, or on your page, your notes page, right here where the arrow is kind of pointing. So in this scenario, a student has taken 100 grams of a unknown substance, okay, and they've heated it, essentially just added heat, okay, and they've made some observations in this chart here, and they've recorded their change in temperature over time. So we can kind of see, at the beginning, we're obviously starting with a solid, and then the student kind of describes how, it slowly becomes a liquid, and then eventually becomes a gas. This time here correlates to the time down here on the graph. So, from 0 to 10 minutes, 11 to 15 minutes, 16 to 30 minutes. So as you're looking at the observations, you can see that their graph is changing accordingly, and it matches up with their observations that are being made. So what you're going to do is take a few minutes, and I want you to work through answering questions 1 through 8. Okay, and so, for example, number 1, you're just looking at the graph, and you're trying to differentiate between kinetic and potential energy. So remember, we've talked about kinetic energy. Remember, kinetic energy is just the motion, the energy of the particles in motion. And so if we think back to our different states of matter, right, we talked about which ones have high kinetic energy, which ones have low kinetic energy. And remember, temperature, right, is a measure of kinetic energy. So our temperature can help us decide, some of these things right here. Is our energy increasing or decreasing or not changing? Once you kind of look at kinetic energy, you're going to skip over to potential energy, and potential is stored energy. So that's kind of energy that's stored inside the molecule, inside the particle. Okay, so read through a little bit about the kinetic and potential energy, and then you're just stating increase, decrease, no change through this chart, okay, just based on what you see in the graph. And then I want you to work through number 8, so that's right here. Okay, so you're going to stop right after number 8. Okay, so pause the video here, take a few minutes to work through yourself. And if you don't get it, if you need to skip 1 or 2, that's fine, but just try to do your best. So now that you have worked through some of those questions, we're going to talk about a few together. So the first thing we're going to look at is questions number 2, 3, and 5. So just kind of check your answers as I kind of talk about it. And if you didn't get it, like I said, you can just kind of fill in as we go. So remember, we said that temperature is a measure of kinetic energy. So if I want to know if kinetic energy is changing, I can just look at the temperature. So anytime my temperature is increasing, right, that means that my kinetic energy must also be increasing. Same thing if my temperature is decreasing, my kinetic energy would be decreasing. And if my temperature stays the same, right, then that means my kinetic energy is also staying the same. So I can look at the graph, and for the most part, my temperature does look like it's increasing. So here, here, it's increasing. But then I have these little points where my temperature line, my temperature is not actually changing, it's staying constant. And so right here, my kinetic energy is actually staying the same. They're not actually gaining any kinetic energy in these minutes here during our phase changes, where the student was noticing that, some of the solids were starting to become a liquid. Potential energy essentially increases pretty much as we go, this way. So it's kind of increasing our whole time. Our forces of attraction, right? If we kind of think back to what we know that solids have very strong forces of attraction, so they're held tightly together, and then our gases have very weak forces of attraction. So we know that our forces of attraction are decreasing as we move up our graph. So for number 6, what we're really wanting to focus on is these little points in our graph where our line stays flat. So probably what you would have thought is like, oh, well, if as I'm melting something, that must mean that the temperature is increasing this whole time that it's melting. But in reality, it kind of pauses. The temperature kind of reaches the point where the solid will melt, and then it kind of stops increasing until you have until your substance is all a liquid. Once everything is a liquid, then the temperature starts increasing again. So we already said how our temperature is a measure of kinetic energy, right? And so if I'm not gaining in kinetic energy here, right, because my temperature is staying the same, what's happening to all of this heat that's being applied to our particles? So remember, over time, we're still applying heat this entire time. So that heat has to be going somewhere. That energy has to be going somewhere. Okay, and what it actually does is it actually, that's what helps increase our potential energy. Okay, so remember, we talked about how solids have the least amount of potential energy and gases have the most. And so what's happening is right here, we're actually seeing an increase in our potential energy. So this is where we really get that increase in potential to carry us over into the next state of matter. So what happens, like we said particles, they're going to store that energy. So we're increasing that potential energy. And instead of using that energy that's being stored to move around faster, it's using that energy to actually overcome those forces of attraction. So remember, we're starting off with particles that are close together, right? And as we get through our melting phase, we want to start kind of seeing those particles spread out a little bit. So we want to break up those forces of attraction between our particles. And the way that we do that is by the energy being applied here. So it's almost like if, you were, like, let's say you're holding on to a bunch of people in a group are all kind of holding on to each other, holding each other's hands, holding each other's arms, trying to stay close together. If I jostle you around enough, push you around enough, eventually you're going to start, losing your grip on each other. So, you're going to be kind of knocked away from each other. And that's essentially what's happening. The energy is increasing so much that instead of, it kind of reaches this breaking point where those particles, they can't increase their kinetic energy anymore. They have to use some of that energy to break those forces of attraction, so then they can spread out like they're wanting to. So if I was to look at some particle diagrams here, okay, and this is the one where you were kind of drawing, your own particle diagram. So as long as it looks kind of similar, that's fine. So here, this is B and this is C, where I'm going from a solid to a liquid. Okay, so I can see that, my energy here, this energy on this flat line here, is being used to break these forces of attraction. So I can see now, I've no longer got this orderly arrangement. They're kind of spreading out a little bit more than they were over here in the solid. When I compare these, let me draw it above so it's not going to get confusing. These two particle diagrams, right? I have a liquid here. And then over this time frame, this amount of energy, right? It has a longer segment. So in order to go from a solid to a liquid, right? We have a small amount of energy because my line is pretty short. Right here, my line is pretty short, but when I start looking from a liquid to a gas, now I have this really long line. So that means, right, it must be needing more energy in order to separate those particles, which if we look at the difference between a liquid and a gas, right, now I have all of the separation between these particles. So that's a huge amount of separation. Whereas if I compare a solid to a liquid, it's not separating quite as much, right? Like some of these are, they're sort of spreading out, but they're not spreading out as much as a gas. So it actually takes a lot more energy to break apart these forces of attraction in a liquid in order to move into a gas than it does in a solid. All right, so number 9, right? So we're down here now. This question is really asking you, do you think this could be the phase diagram for our unknown substance? Okay, and so we want to be able to compare a phase diagram, right, where we are incorporating pressure along with our heating curve, where we're just looking at temperature. And the question asks you to give 2 pieces of evidence. So let's just kind of take a look here. Remember, I know right here, right, this line, this is melting. So if I wanted to get the melting point, right, it's right at about 80. So my melting point, we'll write this, is 80 degrees Celsius, right? And then we know right here, where I'm moving from a liquid to a gas, this is my vaporization phase change, or we sometimes refer to it as a boiling point, right? And so I can follow my kind of graph over. I think it's right at about 218. Okay, so my boiling point is 218. So I can come over here to my phase diagram, and now I can kind of compare. Okay, well, where is my substance melting? Well, melting is going from a solid to a liquid. And remember, we say, right, that, remember our 101, this is our standard pressure. So this is the pressure we want to compare to. And I can't remember, it doesn't specify on your notes a different pressure. So remember, this is my melting, right? Oh, goodness. This line is my melting point, right? This is melting. So if I want to look at the temperature, it looks like my melting point here is 0 degrees. Does that match my melting point on my heating curve? It does not. Okay. The other data point I have is the boiling point, right, where it changes from a liquid to a gas. So my line here, this is where it's vaporizing, right, or turning from a liquid to a gas. So let's move over here with our standard pressure. And then we go down, and this is 100 degrees Celsius is the boiling point, which also does not match my unknown substance. Okay, so my answer, right, would be no, it's not the same. And then my two pieces of evidence is my melting point and boiling point are different. Okay, and if I didn't have my work shown out here, I could elaborate a little bit more about how different they are. But we can see here that we can compare. Okay, so you want to be comfortable comparing those two types of graphs.